Hi, this is Josh from Over the Shoulder Coding, and today I'm walking you through my solution for day 11 of the Advent of Code 2018 challenge. Day 11, Chrono Charge. You watch the elves and their sleigh fade into the distance as they head towards the North Pole. Actually, you're the one fading. The falling sensation returns. The low fuel warning light is illuminated on your wrist-mounted device. Tapping it once causes it to project a hologram of the situation. A 300 by 300 grid of fuel cells and their current power levels, some negative. You're not sure what negative power means in the context of time travel, but it can't be good. Each fuel cell has a coordinate ranging from 1 to 300 in both the x horizontal and y vertical direction. In XY notation, the top left cell is 1, 1 and the top right cell is 301. The interface lets you select any 3x3 square fuel cells. To increase your chances of getting to your destination, you decide to choose the 3x3 square with the largest total power. The power level in a given fuel cell can be found through the following process. Find the fuel cell's rack ID, which is its x coordinate plus 10. Begin with the power level of the rack ID times the y coordinate. Increase the power level by the value of the grid serial number, your puzzle input. Set the power level to itself multiplied by the rack ID. Keep only the hundreds digit of the power level, so 1, 2, 3, 4, 5 becomes 3. Numbers with no hundreds digit become 0. Subtract 5 from the power level. For example, to find the power level of the fuel cell at 3, 5 in a grid with serial number 8, the rack ID is 3 plus 10 equals 13. The power level starts at 13 times 5 equals 65. Adding the serial number produces 65 plus 8 equals 73. Multiplying by the rack ID produces 73 times 13 equals 949. The hundreds digit of 949 is 9. Subtracting 5 produces 9 minus 5 equals 4. So the power level of this fuel cell is 4. Here are some more example power levels that we can calculate later. Your goal is to find the 3x3 square which has the largest total power. The square must be entirely within the 300 by 300 grid. Identify this square using the XY coordinate of its top left fuel cell. For example, for grid serial number 18, the largest total 3x3 square has a top left corner of 3345 with a total power of 29. These fuel cells appear in the middle of this region, of this 5x5 region. So this is the square, these 3 rows. And for a grid with a different serial number, the largest 3x3 square's top left is 2161. So the serial number changes what the power levels are going to be. And then you're going to get a different hundreds digit and end up with a different power level. So we are going to find the XY coordinate of the top left fuel cell of the 3x3 square with the largest total power when our serial number is 4151. So that's the puzzle input. So how are we going to do that? The first thing we need to be able to do is to find the power level of an individual fuel cell. So we wrote that method here by copying over the instructions. So first we need to find the fuel cell's rack ID, which is x coordinate plus 10, and we'll store that as the rack ID. Then we begin with the power level of the rack ID times the y coordinate, save that as the power level initially, and we increase it by the value of the grid serial number, which in our case is 4151, and we're going to pass it in as a parameter along with x and y. We're going to set the power level to itself multiplied by the rack ID, which we calculated in the first line. Then we're going to keep only the hundreds digit. So we're going to do integer division, which is this double divide sign, which means that if we have a float, we'll just cut it off and leave only integers. So we'll divide by 100, so the hundreds digits becomes the 1 digit. So in this example, 949 divided by 100 in integer division would be 9. In this example, it would have been 1, 2, 3, 4, 5 divided by 100 would become 1, 2, 3. Then we're going to do mod 10 and get only the unit digits. So when we have 1, 2, 3, 123 mod 10 is just 3. So that's how we're going to get the hundredths digit out of this number. Then we're going to subtract 5 from the power level and return it. So that's how we're finding the power level for each fuel cell. But we still need to calculate the whole grid of fuel cells. And to do that, we're going to make a class power cell grid that's going to take in the width, the height, and the serial number. So we're going to make a grid, which is a list. And we are going to want to pretty print this grid that we're making. So we're going to make each row that we're printing out its own list. So that's why we're going to start with Y first, and we're going to go down and then put the X on each row. So we're going to make the list that's the height and contain one list for each row. So for starting in range 1 to 300, we're going to append a new list for that row of fuel cells. And then for that row of fuel cells, we're going to append the value of the fuel cell power level. So let's see what it looks like. And maybe we'll use this 3.5 as an example. So we'll do a power cell grid. We can comment all this out. And we'll do a power cell grid of width 3, height 5, and serial number 8. When we run that, we get -3, -3, -3 on the first row, and then the second row, the third row, the fourth row, the fifth row. So this is Y is going down, X is across. Each one, we are printing that inner grid. So for I in range, this is really the Y's, and then each Y will be a row that we're printing. And so you can see 3, 5 here, we get a value of 4, which is what we expected. So we can test out some other power levels if we want. So this is 122, 79 with the serial number 57, and it should be -5. So the one in the bottom right corner is going to be -5. And 217, well, we don't really need a pretty print. We can just do serial number 39. And then calculate the power level of 217, 196, 39. So I did just a little typo. I wrote 296 instead of 196. So we got the right power level. We can check again with the next one, 101 and 153. And serial number 71. And we get 4. So we know that we're finding the power level correctly thanks to the examples. And now we want to make sure that we're finding the 3x3 square correctly. So how do we find the 3x3 square? With serial number 18. So we can initialize our fuel cells, and we can calculate the power of the power level of an individual fuel cell. And for us, that's a constant time operation, O of 1. But when we calculate the power level for all fuel cells, it becomes an O of n squared operation, where n is the size of the grid. And then when we calculate the size of a 3x3 square, we could either do an O of 1 lookup into a stored grid of fuel cells, or we could calculate the fuel cell values for the 3x3 square each time. If we did that, we would be calculating the value of fuel cells on the order of 9 by 300 by 300. So each square has 9 fuel cells, and we have roughly 300 by 300 squares to look through on this 300 by 300 grid. Really, we have 298 by 298, but it's still on the order of 800,000 calculations. If we stored all the values of the fuel cells in a grid and did an O of 1 lookup, it would only be on the order of 300 by 300 or 90,000 calculations for the sums without calculating the fuel cell values, which would be almost an order of magnitude faster. The trade-off here is that we are storing the 90,000 values of our grid in our self.grid, which is an O of n squared storage. But we're trading off some storage for a lot more speed. And so when we find the max 3 square, so the maximum square of size 3, we start with the max power level and location being 0 and 0, 0. And for y, for all the rows, we start going down with y. So for all the rows going down, minus 3, since we have a square of size 3, we don't want to get an array of index, an array out of bounds error. And for the x going across minus the size, we're going to get the square power level by summing the 9 values. So the 9 values are going to be x to x plus 3 and y to y plus 3. So a square of size 3, we're going to do a double for loop over that grid. So, going across x and then going down y 3. And that's going to be 9 values that we're summing, and we're going to return that square sum. So we get the square power level. If it's greater than the max we've seen so far, we store the new max, and we store the new max location as x plus 1, because our array is index 0, but the grid is index 1. And then when we're done with that, we say print the max power level and the max location. And so let's test that out. So grid find max 3 square. And we get that the max power level is 29 and the max location is 3345, which matches up. And if we try with serial number 42, we should also get 30, total power of 30, and a max location of 2161. So we can try it with our input of 4151. So that yields us max power level is 30, max location is 2046. So that was the correct answer for part 1. And now let's move on to part 2. So part 2, you discover a dial on the side of the device. It seems to let you select a square of any size, not just 3 by 3. Sizes from 1 by 1 to 300 by 300 are supported. Realizing this, you must find the square of any size with the largest total power. Identify the square by including its size as a third parameter after the top left coordinates. A 9 by 9 square with the top left corner of 3, 5 is identified as 359. So how are we going to do this? Well, if we did a naive solution for calculating the maximum power level for all square sizes, we would be summing an n by n grid of fuel cells in roughly 300 by 300 minus n squares by n sizes. So it would be on the order of O of n to the 5 or 2.4 trillion calculations, which would take way too long. We can try and optimize our solution by storing previous values of square sums we have calculated. We will start with squares of size 1, then use those to help compute our grid of squares of size 2 with the same top left corner. Then we will use the grid of size 2 squares to help compute the sum of squares of size 3. This seems like the same idea of the naive solution, where you go through and calculate the sums of all squares of size 1, then the sums of all squares of size 2, then the sums of all squares of size 3. But there's a slight difference. And I've made a little visual here for some help. So if you look at this visual aid, the green grid is the grid of square sums of size 3, which is, for our purposes, the total grid. So let's imagine we have a grid of 3 by 3 instead of 300 by 300. The blue grid is the grid of square sums of size 2. So you can see 1, 2, -3, -3, we have a sum of 3. So here, 2, 2, 3, 3, we have a sum of size 10. -3, 3, -4, -1. We have a sum of -5. And then 3, 2, -1, 0, we get a sum of 4. And if we sum this whole square, we have a sum of 3. So normally when you calculate the sum of the square, you do O of n squared summations because you're calculating this entire area. But if you already know the sum of the inner square, so for the example of 3 by 3, if we already know the sum of this inner square, we only need to add these cells on the border, which means that instead of an O of n squared calculation, calculating the sum of the values in a square is only calculating this O of 1 lookup plus n 2n O of 1 lookups. So that's actually O of 2n or O of n. So we cut down of O of n squared operation, finding the sum of a square, to an O of n operation, which means that we can cut down our total scan of all square sums from an O of n to the 5 operation to an O of n to the 4 operation. This is still very costly, but instead of 2.4 trillion operations, we're only doing 8.1 billion operations. The downside, though, is that we are now storing all sums of squares of size 1 through n. So that's O of n to the 3rd storage. So here we're storing all square size 1, all square size 2, all square size 3. We can cut that down by only storing the immediately previous square sums. We don't need all previous square sums to calculate the next square sum. For instance, if we wanted to calculate the square sums of size 4, we only need the previous square sums of size 3, so we can discard the previous square sums of size 2. This means that when we calculate the square sum of size 300 at the end, we only store the square sums of size 299 instead of all previous 300 sets of square sums. So we cut down on our computation for O of n to the 5 to O of n to the 4, and our storage from O of n to the 3 to O of n to the 2, which is no worse than what we're already doing by creating this grid when we initialize our fuel cells. So we have some methods, and I want you to take a look at what finding the maximum square would have looked like. So we still are looping through all the fuel cells, the same as when we were doing it here. But before that, we loop over all sizes. And instead of just subtracting 3, we subtract the size so we don't get an array of out of bounds. Then we found the power level of the square. And that method is here. And that is doing the O of n squared operation where we're looping over all the cells in the square. So what we're doing a little bit better is doing an optimized solution. So we're going and we start with fuel cells as size 1, and then we start the size lookup at 2. And then in the nested square sums, we're finding the max, and we find the local max just for, just because it's fun to know. And then we also calculate the true maximum. And so we're still doing this double for loop, but inside of find square sum, this optimized solution is doing 2 independent for loops. So it's still O of n. So that's how we're saving it. So we're calculating all the cells on the right. So we're calculating this. Then we're calculating all the cells below. And then since we double counted this cell on the corner, we subtract it on line 97 and then return the square sum. So that's what we're doing to save space. And we're only storing the previous square sums. When we get down to the end of the size, we discard it. We overwrite it. So the current nested square sums, like if we're just calculated size 3, that's going to become previous square sums, and then we're going to increment size and start a new nested square sum for size 4. So for each size, we're resetting our local minimum, our local power level that we're looking at, and then we do the double for loop over all squares at that size, and then we simply add the previous square value that we talked about here. So that's how we're saving some time. And I can show you how much faster it runs. So let's run the normal find max square. So it's running kind of slowly. And as the size increases, since the n squared operation of summing fuel cells increases, it gets increasingly slower for calculating the maximum size of the maximum square for each size square. So now we're calculating squares of size 15, which means we were doing on the order of 200 summations per square. And that's very, very slow. My computer is getting pretty hot and it's slowing down, right? So we've just finished 16. We blazed past 1, 2, 3, 4, 5, but now, it's getting pretty slow. So we're stuck on 21, 22, 23. So that's pretty slow, but the max squared optimized is going to be slightly faster. It's still going to be pretty slow, but it's definitely faster than before. So what we're printing out here is where our current size is. So like, let's say we're at 24 and the local power max level is 89 and the local max power location is 220.59. So that means for squares of size 24, the max power level of those size squares is 89 and it's at this location. But the best square size we found so far is 14. And we can see we've already gotten to like calculating size 57. So this is already much faster than the previous method. As we continue increasing our size, we capture a lot more negative values because remember, we are taking only the hundredths digit. So the max can only be 10 and we're subtracting 5. So we have a range between -5 and 4 because it can either be 0 through 9. And then when you subtract 5, it's going to be -5 to 4. So we're picking up a lot more negative values. On average, things are going to be less than 0 in the possible set of fuel cell values. And so as our square size increase, this local max power level is actually decreasing because we're picking up more negatives. So the best square size is 14. And we can wait till it finishes, but you can just trust me. And that is the solution. So it's location 231 by 65 and size 14. So that's how we solve this problem. This is actually quite similar to a problem you might see in an interview where you have a small problem at the beginning where we analyze the 3x3 square. And then when you figure that out, we bring it to a much larger generic solution for all sizes, at which point you do run into computation or storage problems. So people will care that you're able to explain what the runtime is, what the time complexity and the storage complexity are. Thanks for watching. If you like this video, please hit the like button and subscribe to my channel so you know when the next video is coming out. And if you want me to do more videos of this style or HackerRank or LeetCode videos, please comment down below and support me on Patreon so I can find time to do more videos. Thanks, and I'll see you next time.